To support the continuing evolution of science and technology, supercomputers and computational simulation are now key parts of science infrastructure. Today, the fastest supercomputer has a peak performance level of 10 petaflop, about 1 million times faster than a home PC. The 10 petaflop supercomputer K will be available in Japan by 2012. Moreover, it is expected that an exaflop machine, which is 100 times faster than a current supercomputer, will be released by about 2019. Such supercomputers have only been used by a few experts because parallel programming skill and knowledge of computer architecture is required. To provide a useful computer environment ranging from PC clusters to supercomputers that scientists and engineers can use easily and productively, the universities of Tokyo, Tsukuba, and Kyoto have been participating in a development project called the Seamless and Highly Productive Parallel Programming Environment, intended to promote peta and exascale computing. This project is funded by the Japanese government. Programming languages and numerical libraries are very important in helping scientists and engineers in various fields write efficient application programs easily and productively without special knowledge of supercomputers. The University of Tsukuba has been designing and developing a new programming language called Xscalable MP, or XMP for short, with this purpose in mind. For example, let us parallelize this program to run on supercomputers. The program is changed like this so that computation is distributed to compute nodes, and data is exchanged using the MPI communication library. As you might imagine, this is a complicated task. Using XMP, programmers are freed from the tiresome parallelization of a program. This means that a sequential program can be parallelized simply by adding these comment lines. These lines give the XMP compiler some parallelizing hints. The compiler then generates a parallel program. XMP allows programmers to facilitate development of efficient parallel applications and to tune the performance by having minimal and simple notations. XMP was selected as a finalist in the HPC Challenge Class 2 in SC09 and SC10. For scientists and engineers who are not supercomputer specialists, portable, high-performance numerical libraries would allow easy development of programs in their own fields. However, most existing libraries lack both portability and high performance. Moreover, users often do not know which numerical library is the best one for their particular application. Also, even if users can choose correct algorithms, it's not always true that they can use the algorithms easily. In order for libraries to be more effective, users have to choose many tuning parameters correctly. In order to tackle this issue, the University of Tokyo has been developing an auto-tuning numerical library called XABClib. It has three important features: automatic selection of numerical algorithms, its parameters, and automatic tuning of library implementation. More importantly, users are freed from complex parameter selections by using the policy function. Various programs obtained better performance through XABClib. For example, one program reached 10 times faster speeds, and another program reduced memory usage by 98%. Using this library, users are freed from the quest for portability and from worrying about the efficiency of numerical algorithms, and can concentrate on developing portable, high-performance programs on their own. PC clusters and mid-range supercomputers are now widely used to develop application programs. However, PC clusters are different computer environments from supercomputers and depend on features such as batch job systems, file systems, and communication middleware. Dependence on these features causes difficulties in migration from PC clusters to supercomputers. For example, a user program requiring the handling of file I/Os does not always perform well on more than 100,000 CPUs, though it runs well on a small PC cluster. On some supercomputers, files must be transferred between the shared file system and local disks before and after program execution. PC cluster users are not usually familiar with usage. Also, a program cannot run on different MPI library implementations even if the CPU architectures and operating systems are in the same environment. Thus, the program must be recompiled for each PC cluster and supercomputer where MPI library implementations are different. The University of Tokyo has been developing a single runtime environment where users do not need to be aware of various computer environments, and the performance of programs can be scaled up to an environment with more than 100,000 CPUs. By using X-Runtime, various supercomputers and clusters can be available in the same way without rewriting batch JavaScript, file I/Os, and recompiling MPI programs. In the design of a product using computational simulation, the simulation program is executed many times. For example, in the area of drug discovery, a molecular conformation is determined by testing many molecular structures using a molecular dynamics simulation program. Such a process can be generalized as follows. 1. Parameters for the simulation are generated. 2. The simulation program with those parameters is executed. 3. The results are investigated and new parameters are designed based on the investigation. The above process is repeated until the desired result is obtained. This process has been performed manually by users and is thus very inefficient. Kyoto University developed a new script language called Xcrypt to automate such a process. Xcrypt is now used for various applications, such as optimal parameter search for spacecraft charging problems in space plasmas, probabilistic search for the optimal simulation parameter for galaxy simulations, and automatic performance tuning of various software programs. Using Xcrypt, we can automate various kinds of parameter searches by executing a single program repeatedly. In addition, end users don't need to implement complicated search algorithms by themselves because they are provided as library modules. The software introduced in this video is distributed with the S-Core Cluster System software package supported by the PC Cluster Consortium. We hope that the software packages we provide contribute to the productivity of PC cluster users, as well as to that of large-scale supercomputer users, and helps them to move toward peta and exascale computing.